Have you ever trained a machine learning model that looked amazing on the training data, but then completely fell apart when you showed it to new, unforeseen information? It's frustrating experience, right? The core problem here is linked to the most fundamental concepts in machine learning, called the bias-variance trade-off. Our ultimate goal isn't just to memorize our existing data, but to build models that generalize well. Why is this so important? Because real world applications demand models that can handle novel situations, not just repeat what they have already seen. And this trade off is the constant balancing act we face to achieve that. In today's video, we're going to deep dive into bias variance trade off. You'll learn exactly what bias and variance mean and how they relate to underfitting and overfitting, and critically observe and diagnose these issues. By the end, you'll be crystal clear on the theoretical base of bias variance trade off. Let's start with bias. Bias refers to the error introduced by approximating a real world problem, which may be extremely complicated by a simplified model. Its tendency of the model to consistently learn the wrong relationship because it's too simple. Now imagine you're aiming at a dartboard. For example, let's think of this as a dartboard. Now imagine we're aiming at it and we consistently throw our darts. If this is the bullseye, we'll be consistently throwing our darts the top left corner or top right corner. If we observe, our model has a high bias here. Our model, in the sense, our aiming. It is fundamentally flawed and it's too simplistic. So, why does this happen in ML? If your chosen model is too constrained or too basic to capture true underlying patterns in your data, it will have high bias. It makes overly simplistic assumptions. This leads to a common problem called underfitting. So, what is underfitting and what is an underfitting model? An underfitting model is a too simple model that fails to capture the underlying patterns in the training data, leading to poor performances on training and test data sets. Now let's look into variance. Variance refers to the amount that the model's predictions changes if we were to change the training set or train it on different data sets. It's the model's sensitivity to small fluctuations or noise in the training data. Now let's go back to the dartboard example. So if this is the dartboard and this is the bullseye, this time you're trying to hit the bullseye, and on an average, your throws might be centered, but they're scattered around the bullseye. You have a high variance because your throwing technique is inconsistent and highly sensitive to tiny variations or grip releases. Here, the throwing technique symbolizes your model. Now, why does this happen in machine learning? A model with high variance essentially memorizes the training data, including its random noise, specific quirks, and it's too flexible when it encounters slightly different patterns or noise in new data. Performs poorly because it hasn't learned any general rules or it only knows the specific rules of the training set. This leads to overfitting. Now, what is an overfitting model? An overfitting model is a model that learns the training data too well, including its noise and random fluctuations, leading to poor performances on new unseen data. If bias means consistently missing the true relationship and variance means being all over the place, how do we find the sweet spot here? We visualize this by looking at the classic bias variance trade-off graph. In x-axis, we have the model's complexity, and on y-axis, we have the error. And if you look at the graph and the bias curve, it starts high on the left and rapidly decreases as the complexity increases. And now if you look at the variance curve, it starts low on the left, but rapidly increases as the complexity increases. Now you have a U-shaped curve called the error curve or the total error curve, which is the sum of bias square and variance, and an irreducible error. So clearly, the sweet spot of this is the bottom of the U-shaped error curve, or the minimum of this curve. So if you observe the graph, we can say that bias generally decreases with the increasing complexity. Why? Because a more flexible model can capture more intricate patterns, reducing its tendency to make overly simplistic assumptions. If you look at variance, it generally increases with increases in complexity. Why? because a more complex model has more parameters and flexibility, making it more prone to learning the specific noise in the trading data set, leading to a greater instability and inconsistency on new data. So, our objective is to find this sweet spot so that we balance both bias and variance and we get an optimally generalizable model which can give good results on new unseen data. Understanding the bias variance trade off is absolutely critical for building an effective machine learning model. It's not just theory, it directly impacts how well your model performs in the real world. Remember, the goal isn't a model that's perfect on training data, but the one that generalizes well. Grasping this trade off empowers you to diagnose problems with your model, whether it's underfitting due to high bias or overfitting due to high variance, and guides you towards choosing the right technique to address them. Thank you.